Yeah, so welcome everybody to the International Seminar on Automorphic Forum. So today we have Laure Flapan from the Michigan State University that will teach us about cones of Noether-Lefschetz divisors and moduli of K3 surfaces in hyperkähler manifolds. So please.
Yeah, thank you. Thank you very much, Ricardo. And thank you to you guys for this invitation. As I just mentioned, this is my first time speaking in a seminar about automorphic forms. I'm very much an algebraic geometer and very new to the subject of thinking about modular forms at all. So you all are, much more experts from that point of view. So I feel like a little bit of a fraud speaking in this seminar, but I think, hopefully the aim of my talk today will be, not so much to teach you guys things about modular forms, since you know much more than me, but maybe sort of to explain to you some of the reasons why algebraic geometers might be interested in modular forms and some of the geometric kinds of problems that geometers care about that I think can be informed by some of the things that you guys know about. So anyway, that's the plan for my talk today. So it will focus on the geometry rather than the modular forms, but hopefully presented in a way that you guys can appreciate. Yeah, so the setting that I'll work in today, I'm sorry, there's a little bit of background noise on my end. Hopefully you can't hear it too much. The setting that I'll work in today is I'm going to let lambda be an even lattice of signature 2n, and I'm always going to require that n be at least 3, such that lambda splits off 2 copies of the hyperbolic plane. So I always want my lattice to be of this form. And I mean, one can, of course, work in greater generality, but this is the setting I'm going to require for today. And I want to consider what I'll call an orthogonal modular variety to be a quotient of the form, so D mod gamma, where, so D is a symmetric space, which is a connected component of the space of, so Z inside the projectivization of this lattice, such that Z paired with Z, using the quadratic form on the lattice, is 0 and Z bar is positive. Okay, and I'm going to say in a minute why this is the setting that I care about, at least from an algebraic geometry point of view. And then gamma, this group I'm quotienting by. So this D is some symmetric space. And this gamma that I'm going to quotient by is some finite index, let's use white, finite index subgroup of a group that I'll denote O plus lambda. So these are automorphisms of lambda that fix this, this given component D that I've selected of this locus within the projectivization of my lattice. Okay, so this is going to be my orthogonal modular variety, this quotient right here, D mod gamma. And so why, from an algebraic geometry point of view, why is this the setting that I'm interested in, or why do I care so much about these orthogonal modular varieties? So I think, these are a class of varieties that have been studied from the point of view of modular forms for some time, but why might algebraic geometers be in particular interested in these quotients? So from a geometric perspective, right? So the first kind of canonical example of how these orthogonal modular varieties that we see here, maybe I can move my little pen box somewhere else. There we go. Okay, that's better. So of how these orthogonal modular varieties arise naturally in geometry is that, so one of the really fundamental objects that people are interested in algebraic geometry, right? So somehow the first object people usually learn about when they take a first course in algebraic geometry is they learn about algebraic curves, which are the same as Riemann surfaces. right? Algebraic curves of genus G. But the sort of next example that people often see in algebraic geometry is what is called a K3 surface. And so what is a K3 surface? So a K3 surface is a compact Kähler surface, which is simply connected with the property that if I look at the global sections of the space of two forms, of the two forms on this surface, this is one-dimensional and generated by a single non-degenerate form. And so in particular, this implies that if I look at the canonical sheaf on my K3 surfaces, so this is like you can think of this as like the volume form, the global sections of the volume form, or the sort of the sheaf of like two forms really on the sheet on the K3 surfaces. This is telling me that this is trivial. Okay, this property right here that says that this space of two forms is one dimensional. Okay. And so, maybe you can accept that this is that these K3 surfaces are sort of a fundamental object that algebraic geometers are interested in. And then frequently in algebraic geometry, when we consider families of varieties, we consider not just the variety itself, but we consider the variety together with a fixed divisor class, a fixed codimension 1 class on that variety. And usually we require that that class be ample. And so if I let H, if it's ample, I call H a polarization. Or I can also more generally just require that H be what is called big and nef. And what these are maybe doesn't matter for today, so I won't go into the details. But if I choose this divisor class to be only big and nef, I call this H a quasi-polarization. And so how does this relate to the first thing I talked about? Well, if I let the lattice lambda be the perpendicular of this chosen divisor class inside of the integral cohomology of my K3 surface, this gives me a lattice equipped with a quadratic form given by what we call the intersection form on the K3 surface. So that, is equivalent to sort of intersecting curves on the K3 surface. And so what does this lattice look like? In this K3 setting, this lattice lambda looks like 2 copies of U plus 2 copies of the E8 lattice plus, I'm going to require, so if I have this chosen polarization or quasi-polarization H, and I consider its intersection with itself using this quadratic form, this will be some even number, which I'll denote 2D. And so the final part of my lattice encodes what this 2D is. So this right here, this lambda, given by taking this perpendicular of my chosen quasi-polarization, is this is called the K3 lattice. Okay. And so I said that this defining property of a K3 surface was this thing in the pink box, the fact that the space of global two forms is generated by a single non-degenerate form. And so if I consider the map, which takes up the pair of a K3 surface together with this chosen quasi-polarization and assigns to it the space, the line generated by this given class, right? This is the same pink box thing, right? This C omega actually lives inside of this, the projectivization of this lattice lambda. And in fact, one can show that it lives inside of not just the projectivization of this lattice, but in fact, this D, that I defined above, this this symmetric space. Right, so not only does it live in the projectivization of the lattice, but in fact it satisfies these properties of, you know, positive self-intersection and or sorry, zero self-intersection and positive intersection with it, the conjugate of itself. And so the point maybe this, you know, the point is that in fact this gives me a map assigning to a K3 surface S comma H, something in fact, not just D, but I can, this is equivariant with respect to the action of, so a group I'll denote O tilde plus of lambda. So, you know, previously I considered, so these are automorphisms of lambda fixing delta such that I have the added condition that they act just trivially on the discriminant group of my lattice. Okay, so the point, and this map that starts with a K3 surface and assigns it a class in this D mod O tilde plus of lambda, this is called the Torelli map. And it's one of the central starting points of the study of K3 surfaces in algebraic geometry, the fact that this map is actually injective and that it gives us an identification between the moduli space of these quasi-polarized K3 surfaces, and I'll denote of degree 2D, right? So these pairs S comma H such that H squared is 2D. So this moduli space is traditionally denoted by F 2D, and this Torelli map, so via Torelli, we have an identification of this moduli space with this quotient that I've written right here, D mod O tilde plus of lambda. And in fact, this is, in some sense, the definition of this moduli space, right? So what it, you know, meaning now this quotient space on the right parameterizes these pairs of a K3 surface together with a quasi-polarization of fixed degree, such that, you know, any family of such pairs can be encoded by the data of a family inside this quotient space that I've written on the right. Okay. So this is, so I mean, and you will recognize that this thing on the right is, of course, an orthogonal modular variety. As I defined it at the beginning. So what's another geometric situation in which these orthogonal modular varieties arise? So a second example is, you know, so I defined this notion of a K3 surface, and I said that this pink box condition is the defining property of a K3 surface, and that these are, you know, a fundamental object in algebraic geometry. And so in algebraic geometry, you know, people asked, well, how can we generalize this notion of a K3 surface to higher dimensions? Right, this is only for surfaces. We want some kind of class of similarly highly structured objects that exist in all possible dimensions. And, you know, staring at this definition in the pink box for K3 surfaces in front of you, you might have kind of two natural ideas about, right? So I'm going to put this in an orange box. You might have two natural ideas about how this orange box condition could be generalized to arbitrary, this orange box definition, rather, could be generalized to arbitrary dimension, right? So your first idea might be to say, well, if X is n-dimensional, let's consider varieties where that are, you know, okay, so they're compact Kähler n-folds that are simply connected, right? All of that translates immediately from what I wrote up here, compact Kähler surface, compact Kähler n-fold, which is simply connected, right? And so the only sort of mysterious condition about what we want to generalize is this part in the pink box inside the orange box. This condition about the space of global sections of two forms being generated by a single non-degenerate form, right? And your first idea might be that we should say that the space of global sections on my n-fold now of n forms should be generated by a single non-degenerate form. And this condition about being simply connected for a surface should be souped up for an n-fold to say that actually, H naught of x omega px should be 0 for all p less than n. Right, this might be one kind of natural set of conditions that you might guess for how to generalize this definition of a K3 surface. And this is a perfectly reasonable, generalization. And this is a class of variety, which are called Calabi-Yau manifolds, let's say. Right, and so this is probably a familiar term. You probably, this is a class of variety that is very well studied. Particular people in physics care about it a lot. Anyway, it's received a lot of attention. A very reasonable way to generalize this first definition I gave of a K3 surface. But there's sort of one other natural way to generalize this definition that I gave, if we scroll up, which is somehow to just kind of copy this definition, but allow my variety to be of arbitrary dimension. So what do I mean? Okay, say X is still a compact Kähler n-fold, which is simply connected. And then just keep the condition that the space of two forms be generated by a single non-degenerate form, right? Even though now my variety has dimension n, just still keep the condition about two forms. This class of variety, if you consider this set of conditions, this gives you another set of class of varieties that people study, and these are called hyperkähler manifolds. And it turns out that this second definition, in particular, this pink box condition that I've written about the space of global sections of two forms, is a highly restrictive condition that that sort of ensures a lot of structure on the variety. And so in many ways, even though definition number one might seem like the natural generalization of K3 surfaces to higher dimension, it turns out that if you want to replicate a lot of this structure that K3 surfaces have in higher dimensions, that happens in case 2, more so than case 1. So as an example, this condition about this pink box condition, the condition about the existence of this special 2 form omega implies, for instance, that the canonical bundle of such a variety is trivial, and in fact that the dimension of the variety is even. That won't be so relevant today, but it does give you some idea for some of the restrictions on these hyperkähler manifolds. And in fact, these two classes, Calabi-Yau manifolds and hyperkähler manifolds, are sort of fundamental building blocks in the classification of varieties more generally, right? So there's a theorem, which again won't be so relevant for today, but maybe just gives some context for the fact that these are both important classes of varieties, both these Calabi-Yau manifolds and these hyperkähler manifolds. So there's a theorem due to Beauville and Bogomolov, which says that if I have any compact Kähler manifold such that the first Chern class of the manifold, the real first Chern class of the manifold is 0, then there exists some finite étale cover, x tilde, such that X tilde is isomorphic to a product of a complex torus times some product of Calabi-Yau manifolds times some product of hyperkähler manifolds. Okay, so in some sense, you can view varieties in general as being, placed into different buckets according to one way to kind of place them into different buckets is by, looking at kind of their curvature in some sense. And this condition of having trivial first Chern class is somehow equivalent to saying that these are the varieties which are sort of flat. They have like no curvature. And so this is saying that somehow all of these flat varieties are just built from complex tori, Calabi-Yau manifolds, and these hyperkähler manifolds. Okay, so again, this particular theorem isn't important for today, but it's just meant to kind of motivate the fact that these hyperkähler manifolds, which I say really replicate the structure of K3 surfaces in arbitrary dimension, are an important building block in classifying algebraic varieties.
Question.
Okay. Yes, go ahead.
So in the form omega, little omega in your pink box, is it always non-degenerate as a two-form?
Yes, it is always assumed to be non-degenerate, exactly.
Okay, assumed, okay, it doesn't...
Yes,
okay.
that's part of the condition on it, that it must be non-degenerate.
Okay, thank you.
Okay, and I mean, I should say that this isn't relevant for the talk today, but this classification theorem that I've written down, this statement about compact Kähler manifolds with trivial first Chern class being built from these pieces, this is some, really relies on some really difficult mathematics, and in particular, due to results by Yau about existence of Ricci flat metrics. But anyway, this isn't so much the subject today, but the point of introducing these hyperkähler manifolds is just to say that they in many ways behave like K3 surfaces. And that's why they are so well studied in algebraic geometry. And for today, the aspect in which they behave like K3 surfaces that we care about is at the level of their cohomology. So if we, again, consider a pair X comma H, where, X is a hyperkähler manifold now, and H is some choice of polarization or quasi-polarization on the variety, I can again consider the lattice lambda given by taking the perpendicular of this H inside of the integral cohomology of my variety. And then the association of the pair X comma H to the span of this non-degenerate class. This lands in this same D that I wrote at the outset. And just as before, I get an injection. So this is again called the Torelli map, and it is again injective. And so just as before, I get inside of this a quotient of the form D mod gamma, where maybe gamma is a slightly different group, I have an open locus, which I'll denote by M, which is, I can realize as an open locus inside of various of these orthogonal modular varieties, moduli spaces of, quasi-polarized hyperkählers of some given type. So depending on the type, I may have different data associated to my lattice and different gamma. But the point is somehow that we can view these orthogonal modular varieties, or many examples, I should say, of orthogonal modular varieties give a kind of partial compactification. They're not compact, of course, but some kind of partial compactification of these moduli spaces. And so this is really supposed to provide some motivation for why algebraic geometers care about these things to begin with. these quotients. Okay, and so then I wanted to maybe give further motivation then about why algebraic geometers might be interested in saying something about the geometry of these quotients, d mod gamma, right? So this is like motivation to study d mod gamma for algebraic geometers. And I mean, I think a first insight or a first point to make is that in general, algebraic geometers like to study moduli spaces and their compactifications. And they, why do they like to study these moduli spaces? I mean, this is for different points of view. One is just these give sort of interesting classes of naturally defined, algebraic geometric objects, but they also help us. So algebraic geometers in general are just sort of interested in understanding the geometry of moduli spaces more generally. And then also understanding the geometry of moduli spaces helps us understand families of varieties, right? So moduli spaces give us a language through which to understand and formalize families of varieties. And so often knowing something about the geometry of the moduli space gives us new information about families of varieties of the type parameterized by that moduli space. So we'll see an example of this at the end of my talk today. So what are the types of questions that algebraic geometers are often interested in when studying the geometry of moduli spaces? So they want to understand, I mean, the kind of first question you might ask is when a given variety in general has some kind of global parameterization, right? And in, I mean, or at least on an open subset, when you can sort of parameterize it by coordinates in some global way, right? And this is a property called unirationality. Okay, so you might ask when your moduli space is unirational. And a weaker notion is what we call uni-ruled, which says that every point has a copy of P1 through it. Right, so this is saying that if I pick up any point on my variety, I can find a line that passes through it. And this is a weaker notion than being unirational, but it's still quite a restrictive notion, right? In general, so this property of being uni-ruled says that a variety is somehow not that far from being projective, from being rational, or sorry, projective is the wrong word, from being rational, meaning birational to projective space, right? So somehow the variety is very close to being like a projective space if it's uni-ruled, right? And then on the opposite end of the spectrum, we expect somehow that a random variety should be sort of maximally chaotic. And in particular, on a random variety, you don't have this property of having lines through every point. And a random variety, which is maximally complex, which can be formalized in some way to say that it has maximal codiro dimension, it's called of general type. Oops, here. So, or, on the other end, we could say general type. This is, as I said, being general type is somehow maximally complicated. So you could ask, when is your moduli space very close to being like a projective space? And on the other end, when is it maximally far from being like a projective space? And then the other way that algebraic geometers like to study spaces and like to classify spaces is by studying their birational geometry. So studying what kinds of birational maps you can make from that variety to other varieties. And so studying the birational modifications. of that given variety. So in particular, for moduli spaces, you might be interested in studying their birational modifications. And so one way that people study the possible birational modifications of a given variety is to study what's called the cone of effective divisors. On the variety on M, right? So this is the cone given by positive linear combinations with real or rational coefficients of effective divisors on the variety. And this is a convex cone, right? So meaning it looks like, this. Here's my cone. And why is this cone important? There's the cone, right? And it turns out that if I can identify an edge of this cone, this actually induces for me a birational contraction of M, right? So any cone, any corner or edge of the cone that I can identify tells me that, oh, that's a birational contraction that exists for my given variety that I'm studying. Okay, so that if my goal is to understand what kinds of birational modifications of my space exist, I might be interested in identifying all the possible edges of this cone. Okay, so these are sort of the motivating types of questions that algebraic geometers first think about when they encounter a new space.
What's an edge?
An edge is so I mean, I think there's a way to formalize it, but I mean, one way to say it is it's like an extremal ray. So an extremal ray in a cone is says that if I have, so call my edge E, right? And if I have V plus W in E, E is extremal if V plus W in E implies that V and W are both in E.
I see. So it's one-dimensional in particular. Maybe
it's one-dimensional in particular.
Okay.
Yes.
Okay.
Yes.
Thank you.
So one-dimensional, extremal ray.
Okay. And the birational contraction that you are describing has the property that it contracts precisely that divisor?
Exactly. It contracts the divisor that corresponds to that ray.
Okay, thank you.
Okay. So this was all just to sort of motivate the types of questions that algebraic geometers care about, but I promise I will somehow bring in modular forms momentarily. And so if we're interested, this is maybe to motivate somewhat that we might be interested in understanding divisors on these moduli spaces, right? I said we're interested in this effective cone, and it's an effective cone of divisors. So we want to maybe understand the divisors on these moduli spaces. And so for an orthogonal modular variety of the form that I gave, what's an easy way to produce divisors? Well, we can produce divisors via these Heegner divisors. So what's a Heegner divisor? If I take a vector inside the dual of my lattice, so this is inside the tensor of my lattice with Q, I have an associated, actually, let me just denote it with a regular D, an associated hyperplane inside of this symmetric space D associated to my lattice, given by just taking the perpendicular of this given vector. So this defines for me a hyperplane in D. And for this vector, I also have the associated to it sort of two pieces of data. I can associate it to it its class in the discriminant group of the lattice. And I can also associate to it its self-intersection. I can which, because my lattice is even, will be divisible by 2. And then I can sort of look at that in the discriminant group as well. So I can associate to it these two pieces of data. And so how do I define a Heegner divisor? Well, if I fix some mu in the discriminant group and m of the form mu over 2 plus some integer shift, I can consider all of the hyperplanes dv of this form given by v having this fixed class in the discriminant group and this fixed number m associated to it. And it turns out that this sum of hyperplanes can be acted on by my group gamma. And so if I take this quotient by gamma, I get an associated divisor, which I denote by HMU inside this orthogonal modular variety. So this is called a Heegner divisor. And it's a Q-Cartier divisor, if that's something that you care about. Okay. So this is just sort of a natural way to produce lots of divisors on these orthogonal modular varieties just via this lattice theoretic data. And I should add that in general, these divisors are not reduced or irreducible, but okay. So this construction that I've given is, you know, purely lattice theoretic, but we can also view these Heegner divisors very geometrically as well. So the geometric interpretation is the following. If I really have a moduli space parameterizing some algebra geometric objects, whether those are K3 surfaces or hyperkähler manifolds or other kinds of algebra geometric objects whose moduli spaces arise as an open locus inside of these orthogonal modular varieties, I know that for a general one, so if I pick a random pair x comma h inside this moduli space, and I look at its Picard group, so its group of rational divisors, this will be generated, sorry, this is a Z. This will be generated just by a single class, which is this H. But of course, in general, many varieties have other divisor classes on them. And so their locus, where the Picard rank is higher, is a countable union of divisors on this M sitting inside of this D mod gamma. And these are called Noether-Lefschetz divisors. And what do these divisors look like? Well, I can view them as, so that we usually denote them this way, D sub HA. I guess maybe this regular D is more common. The D sub HA, right? And what is this? This is the set of pairs x comma h, where there exists an extra class in the Picard group of x, such that I record the numerical data of the square of this class with itself and its square with the polarization. Okay, so this is some divisor. And it turns out that this set of Noether-Lefschetz divisors, defined in this totally geometric way, is actually equal to the set of Heegner divisors, which were defined in this purely lattice theoretic way. And in fact, there are easy formulas that relate these that are due to Maulik and Pandaripada. Right, so if I hand you a Noether-Lefschetz divisor with this given numerical data D sub HA, I can alternatively write that as a Heegner divisor with the numerical data M comma mu or vice versa. So as an example, if we consider, so F2, which is this moduli space of quasi-polarized K3 surfaces of degree 2. So I said the lattice here then looks like this. Oops, just -2. There. And the discriminant of this lattice will just be Z2, generated by some single class with, it turns out, self-intersection over 2 equal to 1/4, -1/4. Then the Hagner divisor associated to this generator of the Picard group, if I write it this way, right? So this is, I'm recording the class and the discriminant group and its self-intersection -1/4. This, via these easy numerical relations established by Moloch and Pondery-Ponda, I can write as D11. And what is this? I said D11, if I scroll up a little bit, you can see, says that I'm supposed to have a class beta such that beta squared is equal to 0 and beta dot h is equal to 1. And so if I'm interested in the totally geometric picture, what is that telling me? That's telling me that if this is my K3 surface, I have a class beta that looks like this, and it intersects my polarization with degree 1. And this will, it turns out, give me an elliptic fibration on my K3 surface. So this is so this locus is right here, is the locus of K3 surfaces with an elliptic fibration plus a section. And this is traditionally called the unigonal locus. Okay. And similarly, just as one more example to have, if I consider this Hagner divisor in the Noether-Lefschetz notation, this is D00, which means that I have a class beta such that beta squared is equal to -2 and beta dot h is 0. And so this tells me that on my K3 surface, I have what's called a -2 curve, which I can contract. So -2 curves with trivial intersection with the polarization can be contracted. And so I can contract this to get what's called a nodal K3. And so this locus right here, algebraic geometers have studied for a long time in this Noether-Lefschetz language, and this is called the nodal locus. Okay. So,
may I ask a question?
yes.
You look, I think these examples are supposed to be in the case of degree 2 on H. These are degree 2 covers of the plane, if I'm not mistaken, which are
correct, exactly. So degree.
So what is the interpretation of these special divisors?
Oh, in terms of that double cover of
yes.
the plane?
Yeah.
That's a little more complicated. I don't know that there's I think it's just, the K3 surface can be realized in more than one way. So you're right, any degree 2 K3 surface, any point inside of this moduli space, F2, can be realized as a double cover of a plane ramified along a sextic curve.
Mm-hmm.
But I don't know that I don't have an immediate interpretation of these loci that I've listed here in terms of that double cover.
Thank you.
Okay. So the way that all of this begins to relate to some picture involving modular forms is through this theorem. There's this theorem due to Bergeron, Lee, Milson, and Muglin from 2017, which says that if I have a space F lambda given as the quotient as an orthogonal modular variety under the conditions I've listed, with the added condition that the group I quotient by is this particular group of orthogonal transformations that act trivially on the discriminant group, then actually the entire rational Picard group of the orthogonal modular variety is actually generated by these Heegner divisors, which we said in the geometric setting implies that the Picard group is entirely generated by these Noether-Lefschetz divisors. And the proof relies on the connection between Heegner divisors and vector-valued modular forms. And so the idea of this proof, maybe I'm very short on time, so maybe is this theorem. So the idea is that there's this isomorphism between the Picard group of F lambda and the space of vector-valued modular forms of weight lambda, rank of lambda over 2, at the dual of this space. And how does this, so these are as I said, the almost cusp forms of vector-valued modular forms. And how does this isomorphism go? Well, it takes a Heegner divisor, maybe that's hard to see. Yeah, a Heegner divisor with this numerical data m mu, and assigns to it the coefficient extraction functional c m mu that takes a vector-valued modular form f with Fourier Fourier expansion a m mu q to the m e mu, right? So where this is an element of the group algebra of the discriminant group of the lattice, this is m and this is mu, right? And it's a theorem of Borchards that these coefficients can be chosen to be rational numbers. And so it takes this m mu Heegner divisor and associates to it this coefficient extraction functional with the same numerical data. Okay, so if we, and maybe I'll add, and associates to the distinguished divisor lambda, which is the Hodge class on this orthogonal modular variety, it associates to this one minus C00. So this extracts the C00th, or the 00th coefficient of the modular form. And so this isomorphism, the existence of this isomorphism is originally due to Borchards and McGraw, and then its injectivity is due to Brunier, and its surjectivity is the content of this Bergeron-Lee-Moglin-Nielsen theorem from 2017. This relationship right here. And so the point somehow is that this enables us, this isomorphism, for our purposes, really enables us to compute with these divisor classes, right? So we can use the relationship with modular forms to somehow compute things explicitly. So as an example, let's go back to this moduli space F2. If I look at the rank of the Picard group of F2, this is then computable by using this isomorphism and studying the dimension of this space of modular forms. This is the ranks of these spaces are computed by Brunier. And so in particular, in this example, the rank of this Picard group, one then deduces, is 2. And so if we look at these special divisors that I listed before, right, we have this Heegner divisor minus 1/4 L star, which I said corresponded to this unigonal locus of K3 surfaces equipped with an elliptic fibration with a section. And under this above isomorphism, this corresponds to the coefficient extraction functional with the same data. which, so what do I want to say? I want to say that there exists a basis, which I'll call EF, for this space of modular forms, of almost cusp forms, right? Such that if I apply this coefficient extraction functional to this basis EF, for this unigonal locus, I get the vector just 0, 1 inside of Q2. And similarly, if I look at these other loci that I mentioned, right? If I look at this H minus 1, 0 Heegner divisor, which I said was this nodal locus, this corresponds then with this basis to, you know, some particular vector that looks like this in this case. And I also mentioned this class lambda, which is this Hodge class, which is a distinguished class. And if I apply, it's supposed to correspond to minus C0, 0. And if I evaluate that on this EF, I get the vector minus 1, 0. So if I graph this inside of, you know, Q2, I get the following picture. Here's this unigonal locus. Here's this nodal locus. And here's this Hodge class lambda, just using these coordinates. Okay. And so in my final 10 minutes, I'll say something about this first set of problems that I talked about that, you know, algebraic geometers might be interested in understanding when given a moduli space, right? So I talked about that really what algebraic geometers want to know about is like this cone of effective divisors maybe on these orthogonal modular varieties. And these effective cones are generally impossible to compute. They're incredibly difficult to work with. But within here, there's a very natural subcone, which I'm going to denote F and L, which is of F lambda, right? So this is effective divisors, or effective linear combinations, positive linear combinations of the Heegner divisors, or, you know, which we said are equal to these NL divisors, right? So I have some subcone that's generated by these Heegner divisors. And so for both of these cones, there are natural questions we can ask, right? We can ask, are they finitely generated? If so, what do their extremal rays look like? And does this allow us to say anything about, you know, with an eye towards these questions about birational contractions that I introduced at the beginning? And then lastly, you know, the inclusion above begs the question of if there is equality between these two cones. And so there's a theorem due to Brunier and Muller from 2019, which says that if I look at the smaller of these two cones, this cone generated by effective linear combinations of Heegner divisors, this guy is always polyhedral, meaning it's always finitely generated. But their result is an existence result. So it just shows that there exists some finite collection of Heegner divisors which generate these cones, regardless of what the lattice is. And so the theorem that I'll mention today, which is due to Ignacio Barros, Pietro Berry, myself, and Brandon Williams from earlier this year, we actually give an explicit number bound such that this cone of Heegner divisors is generated by the irreducible components, at least, of some finite collection of Heegner divisors, right? So it says, you know, you hand me a lattice, I can tell you how many, like a finite list of Heegner divisors that generate this cone. And in particular, this allows us to compute these cones for many examples. And the reason, or the proof idea, which maybe I'll mention only very briefly, for how one actually obtains this explicit number is that, so maybe recall that if I have, so the space of almost cusp forms of modular forms of the given type decomposes as a direct sum of the span of the Eisenstein series together with the space of cusp forms of given weight. And so if I have a basis for this space of almost cusp forms, with the E living in the span of the Eisenstein series and the F1 through Fn being cusp forms, then this special class lambda that I mentioned, which is supposed to correspond to minus the 0,0th coefficient extraction functional, if I apply it to this basis, I'm supposed to get, or I can choose my basis in such a way that I always get just minus 1, 0, 0. Oops. And so the content of this proof due to Brunier and Muller of the existence of the finite generation of this cone is that they show that the limit as m approaches infinity of these Heegner divisors is always lambda. So that these Heegner divisors accumulate towards this special class lambda, because if I look at the limit as m approaches infinity of these coefficient extraction functionals applied to this basis, this is going to head towards minus 1, 0, 0. And so what this says is that if I'm thinking about, listing out all these Heegner divisors, if this is lambda, then after a certain point, all of these Heegner divisors are accumulating inside of some ball around lambda. And so to make this ball, to compute these cones, we need to make B explicit. And to do this amounts to, we just need to bound the growth of the coefficients of cusp forms in relation to the growth of coefficients of this Eisenstein series E. And while, for you all that study modular forms, I think there's a lot of results that are about sort of the overall behavior of the growth of these coefficients. These are always results that are phrased in terms of like O of something. Like the growth of these things is like O of whatever. But for our purposes, we really needed explicit bounds. And so to do that, we had to use an explicit basis of Poincare series for cusp forms, use the fact that we can express the coefficients in terms of Kloosterman sums and Bessel functions, and then bound those explicitly. And the bounds we get, I think, for you all are very trivial bounds, but somehow we needed to make them explicit. And I'm out of time, but let me say 2 geometric applications of having this result. The fact that so ability to compute this NL cone for these F lambdas. What are some applications as to why, algebraic geometers might be interested in this, which is why we might care about being able to, make these bounds explicit. And so one is that it gives us new uniruledness results for examples for some moduli spaces of hyperkähler manifolds, right? So using the description of these cones of these orthogonal modular varieties, you can conclude new uniruledness results about some moduli spaces of hyperkähler manifolds. And 2, we can use these again to show that some moduli spaces of hyperkähler manifolds are quasi-affine. So this means an open subset of an affine space, which in particular means that families over a projective base families of these hyperkähler manifolds must be isotrivial. So meaning, i.e. the complex structure is constant. Right, so somehow from a varieties point of view, that's telling you that the variety doesn't change in the family. It's like a trivial family of varieties. And lastly, I'll mention this is sort of forthcoming work with Ricardo, which is that we can also use some of these cone computations to identify extremal rays inside of the actual pseudo-effective cone of some of these spaces, examples of these spaces. And then lastly, one can find examples where we have equality of these two cones. So it gives us a way to actually compute this pseudo-effective cone, which in turn we said tells us about birational contractions of our moduli spaces. So, so all of this is to say that somehow all of this comes out of being able to make these computations explicit, and so is a reason why, you know, algebraic geometers care about these cones and being able to work with these Heegner divisors via their relationship with modular forms. So I'll stop there. Thank you guys for listening. Yeah, thanks for